If you have played these instruments, and then you will find that the collision of grains can create liquid sound. I'm not sure if these instruments are inspired by Layton's theory from the book called Acoustic Bubble. In this book, he said that liquid sound are generated by the bubbles. Grains and bubbles sounds like the similar stuff. Let's back to the digital world. If we want to make liquid sound, the first thing is to synthesize a bubble sound. Here is a function given by Case, which describes a gradually decayed sinusoid. In the left side, there is a 3 recorded bubble sounds from individual droplets falling from 0.5 meter high. Right side is a single bubble sound waveform, which is synthesized by Jing by using MATLAB. One bubble is moving close to the water-air interface, and it's rising. The pitch rises along with the movement, and then emits a sound of. Here we get an equation related to time variation. After making a single bubble sound, liquid sound can be simply synthesized by the random sort of different frequencies. I set the initial frequency range from 200 Hz to 3K Hz. Set the time intervals of each bubble randomly as well. Here is the sound. Also, we can add effects. Here I'm doing a convolution with a church impulse response. These simulations roughly synthesize the liquid sound, but not so good in practical applications. If I want to simulate a waterfall, a statistical method is required, because it gives information about the waterfall's features like frequency ranges, bubble numbers, and excitations. A real-time parameterized liquid sound synthesis method is really useful for the video games and automatic Foley. The big challenge is the high degree of freedom of the liquid sound. For instance, the bubble sound synthesis method is just used for the spherical bubbles. For the non-spherical bubbles, every single bubble's tension should be considered. Here is a formula that describes the time-varying shape of the bubble.